So in this example, we're going to take a look at how to find the electric potential for a semicircle or an arc of some arc length, right? We're going to take a look at how to find it for the center. That'll be important. Okay, you'll see. So let's see. This arc length, some questions give you the total charge value. Some questions may give you the charge density being uniform, right? And then the angle. Well, let's just say we have a charge density sigma, or rather, this should be lambda because it's a line effectively. Charge density of, well, Q per arc length S, right? That's what is on this arc. And if we want to find the potential at the center, well, that's effectively a constant radius. So it looks like a Pac-Man here. So, whoops. Constant radius R. Okay. So this is what we do. The potential V, now it's a continuous charge distribution. And so we have, remember, effectively very tiny chunks of charge in this line here. And each of those bits of charge is contributing to the electric potential at that point, right? So what we have to do is come up with an integral such that we add up all of those contributions. And because we're going from the center, it makes our life easy because each of those points will be at the same distance away. So let's see. It's of the form, the Coulomb constant K, times the integral of all of those charges, we'll call dq, over all of the distances from those charges to where, from the charges to the point in question, so the center. In this case, well, R. In general, I'll make it a capital R in a second. Okay. And this is the basic starting point for all continuous charge distributions, right? KQ over R, in this case, it's an integral dq over R. All right, so what should we integrate over? We don't necessarily know the sizes of the dq, so like in previous chapters, we have to put dq in slightly different terms, right? And we do that using the charge density. So over on lambda, we have to solve that equation for q, right? Lambda times s. And s is actually an arc length, which can be rewritten as lambda times r theta, right? And arc length is the radius times some angle, and the angle is in radians, and that's important. Radians is a unitless number. It's not in degrees, okay? So now we actually have a dq in our voltage equation, so we need to take the derivative of this charge with respect to whatever is changing. Is lambda changing? Well, no, in this case, I'm keeping it uniform to make our lives simple. The radius is staying constant. Excuse me. The only thing that changes is theta, right? We're going around. So thus, take the derivative of theta, we get 1, chain rule, d theta, okay? And so now we take this bit and plug it into dq, okay? And we get k times the integral of lambda r d theta over, now we can make that a capital R. And what are our limits? Well, it looks like it's pretty much 0 to 3 pi over 2, right? To keep it general, if this was some random a degree that you might not know, you just leave it as 0 to theta, right? But let's just do 0 to 3 pi over 2, okay? And actually, I've drawn that over. There we go. 3 pi over 2. Okay, so the r's cancel, constants come out, and, well, that's a pretty straightforward integral. 3 pi over 2, and well, that's our answer. That's it. 3 pi over 2 is an angle in radians, so that value won't necessarily affect the value of the voltage, but that's basically it, right? There's one really big step, and that's trying to put the dq into terms of something that we can integrate over. In this case, it was the angle theta. Other problems might be a length, so dl or dx. For two-dimensional surfaces, it may be an angle and a radius at the same time, right? But at least for this semicircle, this is it.